today. All right. So good morning, everyone. Thank you for joining this condensed matter physics seminar. So this morning we have Professor Shuyun Zhou from Tsinghua University to give us this seminar. So before she starts, let me give her a brief introduction. Professor Zhou received a bachelor's degree from Tsinghua in 2002, and then she moved to California to pursue her PhD.
Hello.
I'm sorry. Look, it looks like I got disconnected. Hello, can you hear me?
Yeah, yes. I can hear you now.
I'm sorry. Maybe my internet problem. Okay, I'll start again. So Professor Zhou received her bachelor's degree from Tsinghua University in 2002, and then she obtained her PhD in physics from UC Berkeley in 2007. And then she did a postdoc research at the Lawrence Berkeley National Lab for a few years and joined Tsinghua University in 2012. So Professor Zhou is famous for her work on angle-resolved photoemission spectroscopy for two-dimensional materials, including graphene, HBN, and many other materials. So she has received many national awards. I will not repeat here. So I'll pass the microphone to Professor Zhou. She will give us a seminar on enhanced superconductivity in inorganic hybrid materials. Shuyun, please.
Yes. Thank you, Tsinghua. So I first like to thank Tsinghua for the invitation to give a seminar here. And today I'm going to talk about enhanced superconductivity in this organic and 2D material, 2D hybrid materials. So this is actually my group. So before I start, let me give a brief introduction of research in my group. So in my group, we are interested in two-dimensional materials and heterostructures. In particular, we're interested in experimentally observing the electronic structure E versus K, and also the band structure engineering in the van der Waals heterostructures. So to do that, we use angle-resolved photoemission spectroscopy. This is a powerful tool for attempting all the electronic structure information with both energy and momentum resolved information. And in recent years, there have been major progress in spin resolve and also nano resolve RPS. And in particular for 2D materials, which are small in sample size, for example, the aspholetic flake. So nano RPS is actually very important for this kind of electronic structure study. In addition, in my group, we have investigated a lot of time in developing time and angle resolved photoemission spectroscopy. So this allows us to probe not only the energy and momentum resolved information, but also the dynamics information. So using a combination of RPS, spin RPS, nano RPS, and time resolved RPS, we are interested in reviewing the band structure and the band structure of 2D materials, ranging from both single crystals, thin films to heterostructures. So a few examples of research works done in my group in the past few years, including this band structure engineering of graphene boron nitride heterostructure, these are secondary rock cones. And also we reported the electronic structure of this 30-degree twisted quasicrystalline bilayer graphene. We are also interested in topological properties of the band structure in layer materials, including this type 2 well semimetal, molybdenum ditelluride, and also this type 2 degrad semimetal, platinum telluride diselenide, and so on. So most of the time, my group focuses on this electron spectroscopy, but sometimes, occasionally, we are also interested in material growth. And for example, this molybdenum ditelluride and this platinum ditelluride, the samples were actually grown by my students. And also, we are very interested in looking for new ways to control the material properties. For example, this molybdenum ditelluride is a type 2 well semimetal. And one question that we have is how can we introduce superconductivity into this type 2 well semimetal? Well, this will be the first step if more interestingly, if we can induce topological, if the superconductivity also is topological, then that would be even fantastic. But let's first focus on the first step, namely, how can we induce superconductivity to these topological materials? So how can we induce superconductivity? Now, let's first look at the property of this material, molybdenum ditelluride, from the bulk crystal to monolayer film. So for this layer material, the electronic structure is strongly dependent on the sample thickness. And for bulk molybdenum ditelluride, we know that it's a three-dimensional material. In particular, it's a three-dimensional well semimetal. Regarding the superconducting property, molybdenum ditelluride is a superconductor, but with a very low transition temperature of 0.25 Kelvin. Now for related material, tungsten ditelluride, the superconductivity occurs at even lower temperature. So it's not superconducting even down to 0.1 Kelvin. This is the topological and superconducting property for the bulk molybdenum ditelluride. Now, let's look at monolayer tungsten ditelluride. First of all, the topological property changes from a three-dimensional topological semimetal to a two-dimensional topological insulator. And therefore, quantum spin, novel quantum phenomena, say this quantum spin Hall effect, has been reported in monolayer ditelluride. In addition, by reducing the sample thickness to monolayer, superconductivity with a transition temperature of 0.82 Kelvin has been reported. So this 0.82 Kelvin is much higher compared to the bulk below 0.1 Kelvin. However, it's still quite low, and there are also other challenges. First of all, this one monolayer tungsten ditelluride is actually quite difficult to exfoliate or growth. And also, the sample is very unstable in the monolayer limit. And actually, for many metallic samples, this is a common issue, namely the sample stability. So therefore, a protection layer is typically required to protect the actual monolayer sample. So, so we have, from the literature, we have seen that actually by reducing the dimensionality of the sample, you can actually introduce many new properties. Now, one question that we have is that, can we take another approach to attempt similar or even better properties? For example, say these layer materials, they have a large van der Waals gap between the layers. And if we can use different size of ions to increase the interlayer spacing, then we can reduce the interlayer coupling, and probably we can attempt properties similar to the monolayers flake. Now, the ions that we choose to intercalate are these cations from the ionic liquids. So, so by using this intercalation method, we find that we can actually induce superconductivity to many layer materials. So the questions that we need to address is, first of all, what to intercalate and how to intercalate, and how can we be sure that we really intercalate the ions that we think. And so I'll first give a brief introduction of this method that we use. And in the following, I'm going to give 3 examples of this, the results of this intercalation. First of all, these are tailored topological property and enhanced superconductivity in this intercalated molybdenum ditelluride. And similarly, this method can also apply to tungsten ditelluride, but with a TC much higher compared to the monolayer flake. And so these 2 materials are topological semimetals. We find that actually for other layer materials, say these are semiconducting tin diselenide, we can also induce superconductivity to make this semiconductor to superconducting transition. So, so let's first look at the ions that we choose to intercalate. So we first start with the ionic liquids. Here I show you the cations and anions of the ionic, of a very typical ionic liquids. So this kind of ionic liquids have been widely used for this interfacial gating to inject charge carriers into layer materials. But here we'd like to intercalate these large ions into the van der Waals gap. So how do we know that what kind of ions we intercalate? So we use the electrochemical method with a large, we use an electrochemical method to intercalate the sample, and to confirm the intercalation, we use X-ray diffraction. So here I show you data measured on the single crystal sample with an interlayer spacing of 5.9 angstrom. Now, after intercalation, the interlayer spacing increases to 9.54. And so this is using one ionic liquid. We can use different combinations of cations and anions, and from the comparison, we can find out what kind of ions we have intercalated here. So here, here is the X-ray diffraction pattern using a different ionic liquid with the same cations but different anions. We see that after intercalation, the interlayer spacing remains pretty much the same. So this tells us that the cations probably is the one that is intercalated into the sample. And to further confirm this, we try to compare this intercalation using this other ionic liquid with a different cation but the same anion. And now we can see that when we change the cations, then the interlayer spacing also changes. So this control experiment tells us that here we have successfully intercalated the cations from the ionic liquids. So how different is this compared to previous gating of this ionic liquid? So we know that for this gating called EDLT, this is an interfacial effect. It basically acts only in the region within 10 to 100 nanometer near the interface. And for this gating experiments, typically a lower voltage is preferred the reaction is mostly at room temperature or even lower to trying to avoid electrochemical reaction. Now in our case, actually electrochemical reaction is what we want So we actually use a higher voltage up to like 3 volts, and we use a high temperature by heating this sample to 80 degrees C in order to facilitate this electrochemical reaction. And moreover, another major, so in addition to the difference in these experimental conditions, this intercalation method also has a major difference in that this effect is actually bulk sensitive. It applies to this sample with tens of micrometers thick. So it's actually a bulk effect. So this is the device that we use for the intercalation. So let's see what is the effect of this intercalation to this molybdenum deuterium. So so here is the sample that we use to intercalate. This is a single crystal with 3 millimeter by 1 millimeter by about tens of micrometers. So after intercalation, we can check the X-ray diffraction data, and we see that the original peaks from the pristine molybdenum deuterium sample, they are all gone. And now we have a new set of X-ray diffraction peaks with an interlayer spacing of 11.3 angstrom. So this intercalation changes the interlayer spacing from 6.9 angstrom to 11.3 angstrom. And this effect is bulk sensitive. It applies to the entire bulk single crystal. Now, what do we expect when we increase the interlayer spacing? Well, our theoretical collaborator have done a calculation of the band structure, and they find that actually when the interlayer spacing increases from 6.9 angstrom to 11 angstrom, now the band structure changes from this 3-dimensional well semimetal to basically just like monolayer electronic structure. So here you basically have this quantum, this 2D topological insulator, similar to the monolayer molybdenum deuterium. So this tells us that through this intercalation, we we weaken or even remove the interlayer interaction, and therefore the topological property of the band structure changes from a 3-dimensional well semimetal to many layers of 2D topological insulator. In other words, the crystal after intercalation is effectively a 3-dimensional weak topological insulator. Now, let's also look at other properties. So before intercalation, we know that this molybdenum deuterium has this 1T prime to 2D phase transition at about 240 to 260 Kelvin. And so this phase transition basically changes the stacking angle between the layers from 93.9 degrees to 90 degrees. Now, when we increase the interlayer spacing, now let's see what happens. So here I show you the resistivity measurement as a function of temperature after this intercalation. And here you will see that actually after this intercalation, this phase transition is non-detectable. So it's probably not too surprising when the interlayer spacing is so large and the interlayer coupling is so weak. The stacking doesn't really matter, and so this 1T prime to TD phase transition disappears. Now we also see that after this intercalation, the resistivity drops to 0 at low temperature. And if we zoom in this low temperature region, we'll see that before intercalation, the sample has very low resistivity. However, is not 0. Now, after intercalation, we can reach 0 resistivity with a transition temperature of 7 Kelvin. So how is this 7 Kelvin superconducting transition compared to the bulk and monolayer flake? So here are the results, the reported results for bulk molybdenum diterite. It has a transition temperature of 0.25 Kelvin. And for monolayer flake, the maximum TC is 8 Kelvin. So our intercalated sample shows a similar TC to the monolayer flake, and the TC is much higher than the bulk sample. In addition, one advantage of our intercalated sample compared to the monolayer flake is that it's very stable even in the air. So here I show you the resistivity measurement after storing the sample in ambient pressure for 25 days. And you can see that the superconductivity still remains. So, by this ionic liquid cation intercalation, we can tune the topological and superconducting property of molybdenum diterite. And we know that the bulk is a type 2 3-dimensional well semimetal, is non-superconducting. And now, through this intercalation method, we can change the topological property from this 3D topological semimetal to a 3D weak topological insulator with a TC of 7 Kelvin. And moreover, the sample is quite stable in the air, which is compared to monolayer molybdenum diterite. It is very unstable. So we further look at the superconducting property of this intercalated sample. And here I show you the VI measurement at different temperature. And near the transition temperature, we can fit the data using a power law behavior. And the extract exponent is plotted here as a function of temperature. And at this exponent alpha equals 3, this alpha equals 3 gives BKT transition temperature of 4.6 Kelvin. And this tells us that the superconductivity is behaving to the property. And so we can also take the derivative of this VI curve, and we can get this partial density of states. And here we can see that at zero magnetic field, this critical current is as high as 5 milliamp. And so this critical current, upper critical current is much larger compared to the monolayer tungsten diterite, where the critical current is about 100 nanoamp. So we know that our intercalated sample has many layers stacked together, and our sample thickness is about 50 micron. And so this tells us that we basically have many layers of superconducting molybdenum diterite. And these different layers, they are very weakly coupled. So to further confirm the 2D superconductivity, we also perform this resistivity measurement under different in-plane and out-of-plane magnetic field. We can see that the superconductivity is not so sensitive to in-plane magnetic field. However, it is very sensitive to this out-of-plane magnetic field. And so if we plot the upper critical field as a function of temperature, we can see that this in-plane upper critical field actually exceeds the Pauli limit. So, I have shown you that through intercalation of these cations C2 MIM, we can, by intercalating this cation into molybdenum diterite, we can change the topological property and we can induce superconductivity. Now, one question is, does this method apply to other ionic liquids? And does it apply to other materials as well? So here we try to use a different size of size of cations in the ionic liquid, but here they still have this. They are still in the same family, but with different lengths of carbon chains here. So here we can see that these cations can also be successfully intercalated into molybdenum diterite, and we can also see superconductivity with TC of 6.5 Kelvin. Now, even if we try other families of ionic liquids, we find that we can also intercalate these cations into the layer material, and here the TC is somewhat different. So, so I have shown you that by intercalating these different organic cations into molybdenum diterite, we can obtain these hybrid topological materials, and we can induce superconductivity with TC up to 7 Kelvin. So how about other samples? Now, one thing that I would like to try is this tungsten diterite. It overall has very similar property to molybdenum diterite, but with some small difference in that the monolayer flake shows this quantum spin Hall effect. So here is the sample, and the X-ray diffraction data tells us that we can completely intercalate the bulk single crystal, and we can increase the interlayer spacing to 10.5 Kelvin. Now, when we measure the resistivity at low temperature, we see that this intercalation also leads to superconductivity with a transition temperature of 2.3 Kelvin here. So this 2.3 Kelvin is somewhat lower compared to intercalating molybdenum diterite. However, compared to tungsten diterite, this monolayer sample, the TC is only 0.82 Kelvin. So here we actually have a TC much higher than the monolayer flake. So this tells us that this intercalation method not only gives properties similar to monolayer flake, but sometimes we can achieve properties even better than the monolayer flake. And we find that this superconductivity in this intercalated tungsten diterite also shows very anisotropic response to applied magnetic field. So it's much less sensitive to the in-plane magnetic field, and is much more sensitive to the outer plane magnetic field, suggesting that superconductivity is also highly two-dimensional. So what is the mechanism of the superconductivity? Well, we note that these cations, they carry charges. So one possibility is that perhaps these injected charge carriers could be important for the superconductivity. And also at the same time, we actually change the dimensionality or the interlayer interaction of this intercalated sample. So these are the two major issues here. And for the moment, our preliminary results show that this interlayer spacing probably plays a more important role. And so other possibilities include, say, reduce this change in the screening of electron interaction, or maybe electron phonon interaction, or even electron phonon interaction with phonons from the ionic liquids. So the superconducting mechanism is at this moment is not clear yet, and I hope that more experts in this field will become interested in this material and look into this superconducting mechanism together with us. So by intercalating these large size organic cations, we can we can tune the topological property and superconducting property of the material. So the next example that I'm going to show you is this tin diselenide sample. So this sample is very different from the molybdenum ditelluride or tungsten ditelluride in that it is a semiconductor. So for such a semiconductor, can we induce superconductivity to this material or not? So we apply the same electrochemical intercalation method, and we can increase the interlayer spacing from 6.15 angstrom to 9.82 angstrom. And before intercalation, resistivity measurements show that the sample, the resistivity increases dramatically at low temperature, showing that it is a semiconductor. Now, after intercalation, we see that there's a transition to zero resistivity with the transition temperature of 6.9 Kelvin. And also, the superconductivity shows very anisotropic response to applied magnetic field. Here, this upper critical field does not go beyond the Pauli limit in our measure temperature range. However, if we extrapolate this line, it seems to suggest that this upper critical field may go beyond the Pauli limit if the temperature is low enough. Now, how is the superconductivity of this intercalated tin diselenide compared to other superconductivity induced by other methods? So here I show you a table with summary of superconducting tin diselenide using different methods ranging from intercalation, gating, or thin films, and so on. And here we show that our intercalated tin diselenide has a quite high transition temperature of 6.9 Kelvin. This is much higher compared to the gating method, and in the same time, it has very high anisotropy. So here, this is the in-plane magnetic upper critical magnetic field over this outer plane magnetic field to indicate how anisotropy it is. And here we see that this intercalated sample is quite anisotropic compared to intercalation using other ions before. And moreover, the sample is again very stable in the air. So by using this intercalation method, we can obtain high TC and strong anisotropy at the same time. Now, so what happens? We perform RPS measurements to look at the electronic structure before and after intercalation. So before intercalation, we see that within 1 eV below the Fermi energy, there are no bands. This is agreement with the semiconducting property. Now, after intercalation, the RPS data quality becomes somewhat less because of some disorder introduced. However, here we can see that near the Fermi level, there's some intensity here. And this intensity corresponds to this peak in the density of states near the Fermi level. So this tells us that this intercalation actually induces charges to the sample. And this electron doping is probably quite critical to the superconductivity here. So to further confirm that, we perform measurements on different intercalated flakes, which have different amount of intercalating ions or different carrier concentration. And we can extract the transition temperature, TC, as a function of this carrier concentration. And here we can see the phase diagram here, and there's an optimum carrier concentration with the highest TC of 6.9 Kelvin. So this tells us that these the charge carriers induced by these intercalated cations is probably the main reason for this superconductivity here. So by using this electrochemical intercalation method, we can induce this semiconducting to superconducting transition, and it shows a very strong anisotropy with reasonably high transition temperature. So, I hope that by using these three materials as an examples, I can convince you that this intercalation method is actually quite universal. It applies to many different layer materials. We have also tried tantalum, disulfide, graphite, and so on. And this intercalation method works for all those materials. So, so here is my summary. By using this new approach of this electrochemical reaction method, we can intercalate these large size organic cations into the interlayer spacing in the layer materials. And by through this intercalation method, we can obtain these hybrid materials with new properties. So this method actually is very nice. It applies to many different kinds of organic cations in the ionic liquid. It also applies to many different layer materials. And this intercalation method has a dual control. It not only controls the interlayer interaction, but also at the same time, it injects carrier densities into the materials. And as we know, in the research of 2D material in the past 15 years, these are the two most important control knobs. These are dimensionality or interlayer interaction, and the second is this carrier concentration. So here, by using this intercalation method, we can simultaneously control both interlayer interaction and carrier concentration. And such intercalation can lead to new topological properties. For example, this superconductivity that I show you here, but probably more interesting properties can be discovered in other materials as well. So with that, I would like to conclude my talk here and thank the people who have contributed to this work. So this intercalation project is mostly done by my student Shuyun Zhou and my postdoc Awo Bagley. And this work is in collaboration with Yu Group and Wenhui Duan Group at Tsinghua University. And with that, I'd like to stop here and thank you for your attention.
Okay, Shuyun, thank you so much for your nice talk. We actually have quite plenty of time for discussions. I would like to invite questions from the audience.
Hi, can you hear me?
Yeah, yes.
Hi, Shuyun. Hi, I'm Albert Chia. Very nice talk. Thank you very much. So I want to ask whether you have measured magnetization data or specific heat data from your samples.
Yeah, we did. Yeah, I just replied to your email. So it's actually quite surprising that from this magnetic susceptibility, it seems that the calculated superconducting volume fraction is somewhat surprisingly low. So this filamentary superconductivity is one possibility. But one thing that I was thinking is that this molybdenum diterite actually it's very different from many other materials. As we know that it's a almost charge balanced material. It has nearly the same amount of electrons and holes. And I am not sure how that would affect this superconductivity. So, so perhaps here the superconducting mechanism could be quite different. And indeed, in our measurements, we find that the superconductivity in this material does not seem to depend sensitively on the charge carrying concentration as compared to the tin diselenide. So even though here we achieve superconductivity using the same intercalation method, but I think that the superconducting mechanism probably could be quite different. And I would certainly encourage more experimentalists and theorists to look into this. I think this superconducting mechanism is certainly an interesting topic. And also, when in this intercalated sample, is it possible to have topological superconductivity or not? Is another important question.
Has anyone measured specific heat?
Measure?
Specific
Sorry?
heat capacity.
Heat capacity, no, we don't have a heat capacity measurement yet. Yeah, no.
Okay, okay.
Albert, yeah. Okay,
Yes.
okay. I thought there's a microphone problem. All right, do we have, yeah, go ahead.
I have a question. Hello, my name is Christos. Nice to meet you. Thank you for the talk. I am actually quite novice in this material, so I don't know much about the magnetism of the pristine phase. So could you please remind me, at least for one of those that showed enhanced superconductivity when it becomes more 2D-like, when you intercalate, what type of magnetism you have, if any?
You mean for this last material?
Yeah.
This one here. Or okay. So for SN for this tin diselenide, there have been quite a few different methods to introduce superconductivity, say intercalation of these cobalt ions or lithium, or monolayer field with electron doping. So, and this table summarize the superconducting property of all these materials. And using different methods, you may achieve different TC or different interlayer spacing and different anisotropy. And we find that for our intercalated sample, the major difference is that our sample is quite stable. And at the same time, here, well, the comparison of these two columns is actually quite interesting. You will see that for this interlayer spacing, delta D is actually very similar to these other intercalated ions. However, the superconductivity is much more anisotropy, and this seems to suggest that the ions act very well as an inert spacing layer. So it seems that these intercalated ions does not interact very much with the tin diselenide layer. And we think from the RPS measurements and also the transport measurements, we believe that this carrier concentration actually is directly related to the superconductivity. So you inject charge carriers into here. And this mechanism, I believe that this charge carrier concentration applies to all these gating intercalation or MB thin film. So for the MB thin film, the graphene sample is grown on the monolayer sample is grown on graphene, and there could be some charge transfer from graphene.
The reason I ask is because actually there has been a lot of work in the past 40 years on other superconductors, mainly on layered superconductors such as copper oxides, where people were puzzled and are still puzzled on the TC dependence on the interlayer spacing or on the C-axis interlayers interaction. And in fact, there was this good material, mercury barium calcium copper oxide, where people could insert up to 5 layers of copper oxide. So the number of layers of copper oxide increases, TC increases up to 150 or 60 Kelvin. But there is a maximum. So there is a dome as a function of interlayer spacing in TC. So TC goes up as you insert more and more layers. And at some point, it starts to go down again. And this has puzzled the community a lot. So then the idea was that anisotropy is very important. So the more the isotropic the compound, the lower the TC. And this brought back again the discussion of spin fluctuation theory in heavy fermion compounds that are even older. And people had found that if you have a heavy fermion compound, especially if you think of it in terms of spin fluctuation theory, TC would be lower in the isotropic compound. And when you do the measurements in a tetragonal compound, which is a kind of semi-anisotropic, TC rises by a factor of 2 or 3, sometimes 10 times. So the idea was that, the question was that why would there be robust pairing if you have a quasi 2-dimensional structure as opposed to a 3-dimensional? Could it be that the amplitude of the oscillations in the interaction is stronger because of low dimensionality? So the question actually, I wonder, in your compounds, could it be that actually the oscillation, the amplitude of your oscillations in the interaction channel leading to superconductivity is enhanced as you go to lower dimensionality and is not merely charge carrier concentration effect or topological effect?
Well, you raised a very interesting point. Yeah, I think this you mentioned about this intercalation of cobalt oxide to this magnesium borate. So actually, similar behavior also occurs in the cuprate superconductor.
It's the cuprates that I mentioned, not the cobalt oxide. It's the copper oxide layers. Yeah, the cuprates.
Oh, okay, the cuprate. Yeah. So yeah, that's certainly something interesting to investigate. And actually, one puzzle that we have for this superconductivity in this molybdenum diteroride is exactly this. We have measured quite many samples, and they may show a different carrier concentration, but the TC doesn't. We cannot find correlation between TC and carrier concentration, like the one that we have here for this tin diselenide. So the physics for this superconductivity in these two materials is actually very different, and we are quite puzzled. And so you mentioned about spin fluctuation as a possibility, and I'm not sure how that could be related to here, but we are also trying to change the interlayer spacing of this molybdenum diteroride.
I wasn't trying to infer that spin fluctuation theory is actually in charge of conductivity here. What I'm saying, I was just trying to, I'm really impressed by the correlation that one can see between the change in the dimensionality of the system and the variation in the superconducting transition temperature in a fashion which is very similar to the cuprates, but also to some of the heavy fermion compounds. And I just wonder what could be the correlation here between these very different systems and yet a quite similar behavior. And I wouldn't worry so much about the doping dependence of your charge carrier, because the question, of course, is which carriers do participate and which don't. So that's another thing. But yeah, it was just the observation, which I find fascinating.
Yeah. Thank you for your comment. Thanks.
Shuyun, sorry, I have another question. For the, can you show the slide for the RT graph of MoTe2 and intercalated MoTe2? Yeah, so, okay.
Yeah.
So I noticed that for the non-intercalated MoTe2, the resistivity is kind of pretty flat, and then at TC it drops. But here I can see that just before TC, there's a pretty sharp rise in the resistivity. Is there anything interesting that's happening there?
So we have met. So you're mentioning about this drop here and this flattening here. So we have measured many different samples, and so if the measurement, if the sample is high quality, we basically will see this kind of behavior, this flat behavior here. Yeah, but sometimes if as you know, this intercalated sample cannot be perfect, and sometimes probably there could be some other domains. Yeah.
Okay. Thank you.
One more question, sorry.
Yes.
There was this report by Uemura's group from Colombia on bulk molybdenum telluride using μSR, I think, where they claim of the discovery of long-range magnetism at low temperature in molybdenum telluride, molybdenum diselenide, but they were bulk systems. And the temperature, I think, was like below 40 Kelvin, where they observed bulk magnetism in these semiconducting dichalcogenides. So do we understand, do people know what sort of magnetism you're talking about?
Well, actually, this is actually new to me. Yeah, the magnetism in this bulk molybdenum telluride. I don't know about this.
I think it was it's on archive since 2017 it was published in Science Advances in 2018 by the group of Uemura from Colombia.
Okay, I'll look into that. Yeah, that's actually quite new. Yeah, quite interesting magnetism in this material.
Yes, I find they say they found this long-range magnetic order below 40 Kelvin and 100 Kelvin, the bulk semiconducting molybdenum ditelluride and molybdenum diselenide using μSR and SDM and DFT.
Okay, thanks. Yeah, thanks for pointing that out.
Okay, thanks, Christos. Okay, I wonder if your cations actually has a certain configuration. I wonder whether this matters for the superconductivity you observed, whether there are certain rotations or the functional groups pointing towards certain directions, whether affect your superconductivity.
Yeah, well, you raise a very interesting point about the alignment of these cations. So yeah, we'd like to know how they align or not aligned. But at this moment, we don't have that kind of microscopic information yet. Now, we do speculate that since these are ions and we use electrochemical method to intercalate them, there's probably a certain arrangement of the most stable alignment. But at this moment, yeah, we don't know how they actually attach.
Don't know. Okay.
Align.
Okay.
Here. Yeah.
But mainly is the it's positive charge, right? Most of the functional groups you're using.
Yeah.
Okay. The tin diselenide sample you mentioned as a semiconducting behavior. The original, the starting material, is this slightly N type or P type? Whether it matters to the results.
whether it's slightly N-type or P-type.
Yeah.
It doesn't seem to really matter. But well, at this moment, we're trying to control this carrier concentration more precisely. But at this moment,
Okay.
yeah, this control is not really to that extent yet.
I see. All right. So do you have further questions from our audience?
Hello.
Yeah, go ahead.
Professor Zhou, thank you for a wonderful lecture. I have two questions.
Yes.
As we know, in two-dimensional materials, monomer iron selenide has higher TC than bulk, and also it is similar for TMD. So my first question is the interlayer interaction always a destructive factor for superconductivity? And my second question is, there are also some cases high pressure makes the superconductivity, for example, H2S. And high pressure usually increases the interactions. So how to understand the different roles of these interactions in superconductivity? Thank you.
Oh, okay. So your first question is regarding whether interlayer interaction is helpful or bad for superconductivity. Yeah, it seems that it's somewhat easier to get superconductivity when you reduce the dimensionality. Say the example that you gave, this iron selenide or this molybdenum diterite that we have here. Yeah, it seems that this reduced dimensionality could be useful. Now, whether, well, probably, well, the reasoning that I could think of is probably that at low dimensional material, it's easier to get somewhat higher density of states. But this is not always the case. So, but from experimental observations, it seems to be true that this reduced dimensionality from 3D to 2D is usually favorable for superconductivity. Now, your second question is regarding this superconductivity in this high pressure experiments, say this sulfur dihydrogen and so on. Now, I think this is a new area, and so for those molecules and gases, what is the mechanism of this superconductivity? They could be very different. They could be quite different from these hard materials that we study in condensed matter physics, say this iron selenide or this molybdenum diterite. So yeah, I don't have a good answer to that, the connection between that and the hard condensed matter materials that we study here. I think this is still a very new area.
Okay, so if we do not have further questions, please join me thank Professor Zhou for the wonderful talk. Shuyun, thank you so much.
Thank you. Thank you.
Thank you, Professor.
Thank you so much.
Thank you. Bye-bye. Thanks.
Yeah.
Bye.